Zach is a project manager with Ayres Associates in the Geospatial Division. Zach specializes in leading large-scale orthoimagery and Lidar projects for clients across Wisconsin and nationally in the public sector and utility markets. He's a program manager for the WROC initiative and has been a WLA board member since 2016. Rob is chief surveyor with SEWRPC and performs county surveyor duties for a number of counties in Southeast Wisconsin. And Zach, I just saw your slides disappeared, FYI. Rob was also the WLA Friend of Land Records Award recipient in 2018. And your slides are back, Zach. And if you'd like to take it from here, go for it.
Okay, thank you, Jim. Can you hear me okay?
Yep, coming through fine.
Okay, great. And Rob, let's just do a sound check for you as well.
I can hear you. Can you hear me?
I can hear you.
Good deal.
Okay, great. Today we will be talking about the SEWRPC Milwaukee County High Density Lidar project. And we'll get started here. Okay, a little bit about what we're going to cover today. We're going to go over the project background. We're going to discuss the actual collection and processing of LiDAR data. Then Rob's going to share some point density comparisons between this high density data set and previous lower density data sets. Rob will also be sharing tested accuracies against ground control. And then we'll talk about some of the stakeholders and derived products that came out of the project. So LiDAR has come a long way in the last 15 years. And if you just look at specifically in this region, going back to 2010, projects were undertaken at less than 1 point per square meter. And if you step 5 years forward, projects were acquired at 2 points per square meter. So doubling that point density. And I'm talking about single swath point density. And then you flash forward to just this past year for this project and advancing all the way up to 30 points per square meter. So significant advancement in terms of point density in just the past 10 years. And really you're looking at initially with those 1 point per square meter projects 10 years ago, you're looking to take on the challenge of defining the ground, bare earth terrain, and sort of looking at an alternate approach to a photogrammetric DTM compilation type project where you can actually go and collect LiDAR data at a density on the ground where you could generate, let's say, 2 foot contours very accurately. So now once we expand beyond that, we're looking at higher point densities on the ground, let's say in 2015, but we're also now looking at better definition above the ground. So we're able to map the ground at a very highly accurate level, but now we can see detail above the ground. And we start looking at things like extracting, let's say, 2D building outlines from that 2 point per square meter data. And then once again, we're looking at this dynamic technology that continues to advance to the point where at 30 points per square meter, you can see even in the graphic on this slide, the level of detail and the returns that are being collected, even on transmission line conductors, for example. Rob, do you have anything to add to that?
Other than the fact that, I've been working with LiDAR since probably the late 90s, and it is amazing that the technology that we've seen developed and emerge over time has been, amazing. That's kind of my one word answer with LiDAR. As far as just with these last probably say 10 years or so, we looking at it from a high density kind of area, it was always thinking about it. You got to fly it with a helicopter or maybe terrestrial, was the only way you would actually be able to collect it. So, and now with, newer ways and newer technology, there's all options that are available to now support that in more of a wide area collection. So that's just wanted to throw that out there too.
Okay, so if we take a look then at what sort of technologies have allowed us to take on a project of this density across this large of an area, one of the things that comes to mind right away is the LiDAR sensor. So this is a Regal VQ1560i sensor, and you're talking about bringing in a scan pattern, dual channel LiDAR sensor that has an 8-degree forward and aft comparison between the sensors. And if you look at that scan pattern in the graphic and how that's offset, and then you look at where those dual channel sensors are collecting data in that 8-degree offset, you can see the density of LiDAR that's collected. That's a very high signal to noise ratio, which is a good thing. That allows for better definition of attributes in the ground. So you can have a very high density point cloud that has a lot of noise, and then it makes it hard to find those features in that point cloud. But in this case, the sensor has a very high signal to noise ratio. And then if you compare that to, maybe you've heard of Geiger mode LiDAR or single photon LiDAR, those are capable of collecting very high density, but they tend to have quite a bit of noise associated with them. Rob, would you like to add anything?
Yeah, the 8-degree forward-looking aspect was intriguing in the fact that now you're looking more in an oblique perspective instead of just say a straight down, top down aspect, which allows now to take, as we're collecting data, not just looking directly at topography, but now having the ability to look at what's above and the above ground feature and the walls associated with it, or say a pole or other above ground features and aspects. The other aspect, just to mention real quickly, as far as with the Geiger mode versus, say this, is it has the multi-return aspect. So when you're looking at a tree or an object where the light can continue to pass on through, you're able to get more points underneath that surface. The density still, is exactly the same with Geiger versus, this Regal system, but it actually has the capability of now further penetrating, that say vegetated area.
Okay, so if we start to take a look at the project background here, planning started back in early 2019, really posing the question, what level of point density can be achieved across an entire county. And of course, what better county to use as the first project in the state than Milwaukee County, being the most urban area and most urban environment. It really made sense to start here. And we had to ask those questions and make those key decisions kind of early on about what sensor type it's going to take. What point density are we confident that we can achieve? Because there's significant time involved in acquiring and processing the data. We have to understand what base deliverables we want to produce and what the expected accuracies are of those deliverables. And we also, one of the key drivers in this project for the county and for SEWRPC and for the stakeholders was, what additional data can be derived from the point cloud. So once all of this was determined, we came up with a solid technical approach. We undertook the flights in partnership with Quantum Spatial in the spring of 2020. And then we took that data at Ayres and processed out the data and produced deliverables and submitted those in the fall of 2020. So again, if you just take a look at the LiDAR collection components, QSI brought in the 1560i sensor over 52 flight lines across the county, flying on an average of about 3,300 feet above ground level. It was planned with full 60% side lap, so we're ensuring full double coverage across the ground. And then, of course, we're achieving this 30 point per meter point density. And ultimately, the data was acquired on 3 lifts between April 2nd and 3rd last spring. Of course, the ground control is an important aspect of a high density LiDAR project like this. So this map shows you 24 locations that our surveyors collected across the county. using survey grade GNSS. And, you know, this data was collected in state plane coordinates, NAD 8311, and a vertical datum, and a VD 8812B. So really the ground control for calibration is an important aspect because you're comparing the raw LiDAR point cloud that's collected from the sensor, and you're going through a calibration process, and then you need to compare that to very accurate real world coordinates. And ultimately in the yellow, you can see that the comparison of the calibrated point cloud to these 24 calibration points resulted in a vertical RMSE of just under 6/100ths of a foot. And so this is the first step to check the accuracy, but ultimately for comparison, we're needing to achieve 0.16 feet in terms of deliverables. So at the calibration process, we're well on our way towards that. Then we go into the LiDAR processing steps. Again, calibration, we take that calibrated point cloud and run an automated ground macro to determine the approximate ground locations and classify them as such. And then a very manual intensive ground editing process with our technicians, as well as a point classification process. One of the more manual parts of the project certainly is the hydro and bridge brake line collection in a very complex environment. Ultimately, we're generating deliverables, the classified point cloud in LAS version 1.4 format, a bare earth DEM at 1 foot pixel resolution. So again, that's a very high resolution for the DEM. You know, previous projects would have been a 5 foot pixel DEM. And then the hydro brake lines and bridge brake lines are also a deliverable. So some of the more complicated parts of this project certainly were the bridge brake line environment, the zoo interchange, the Marquette interchange, you know, properly identifying and removing those bridge decks with bridge brake lines so that the DEM interpolated properly was a very challenging environment to work in. The ground macro, based on the size of the data, it took 3 days to run on 3 processing machines. And then a highly detailed manual process of editing that ground to deal with decks, patios, retaining walls, and bridges to make sure those things aren't retained in the ground. Ultimately, how much data? There's 2 terabytes of raw data, and we ended up with just over 1 terabyte of deliverables for those base products. Okay, and with that, I'll hand it over to Rob for some comparisons.
Okay, so I guess a couple things, you know, that, as you know, thanking Ayres, you know, and as far as for supplying the information and working with us with this new project and having the ability to help evaluate it right off the bat. So we took, you know, initially with the commission, as far as we took a kind of a 3-prong approach, you know, as far as, you know, assessing kind of the information as it was initially collected and pre-processed. So the first part was just, you know, evaluating the accuracy and how things were fitting and meeting, and then a full tile review, and then kind of, you know, what we wanted to do is more, I think what everybody's interested is evaluating what is 30 points per meter squared, you know, and what does that mean, or what does that entail? So we wanted to do just some evaluations. So with going to the accuracy assessment, we took a different approach than traditional LiDAR. So you can go to the next slide, Zach. So what we did was we independently went out and surveyed 34 hard and soft, you know, ground points, you know, through the county independently. So Ayres had no knowledge of where these points were located. And what we did was we were only strictly providing them approximate coordinates. This time, instead of just looking at it for vertical, we actually gave them the task of, we wanted to evaluate the horizontal. So we went out and even surveyed horizontal points. And in this process, and just to really try to understand or better understand the accuracy of what was achievable with this high density LiDAR. So this was a little bit of a different step and a different approach. So in that first initial accuracy assessment, we took the horizontal, gave them approximate 10 feet of the actual surveyed position. And Ayres went out and measured each of those individual as far as photo IDs. We did provide pictures and locations, so you can go to the next slide, with varying locations as to what was being surveyed. That they in turn provided us the measured value, and then we compared the measured value against our survey value. Once that was completed and everything was analyzed, we then gave them the aspect of, now we gave them the horizontal survey location. Then they were to provide us the elevation. So, and we also then at that point provided additional as far as vegetated points, as far as grass points and wooded points and, high grass versus, short grass. So it was to be more comprehensive, to really truly understand the accuracy of what can be achieved in a high density LiDAR data set. So the results, you can go to the next slide. So the results, apologize, it's very difficult. Hopefully, that everybody can just be able to zoom in on say a PDF or a slide. But the results were absolutely amazing. I was kind of blown away. So what we have is horizontally, which that was the first I've done where I've independently tested in my experience. And we were able to achieve with these blind results an RMSE of basically of half a foot in an X and a half a foot in a Y, with at 95%, it was 1.1 feet or 1.2 feet. So it achieved, the results were really, really solid. And I was impressed by the overall accuracy that what could be achieved with the features that were identified on the ground, the independent, points. Furthermore, the vertical was even better as far as you can see with all the hard and soft points, the result was 0.2 of a foot as an RMSE at 95%. So everything that I was excited about with the high density aspects, was confirmed, as far as with especially knowing that it was completely independent. It was not, done, they were done and hidden. So they were, the results were really controlled to make sure and ensure that the accuracy of what they were reporting was in fact true. So that would pass with flying colors. So excited about the accuracy of what could be achieved with a high density data set. So we moved into the next aspects. So the next was to evaluate a couple sample locations. Ayres then provided us the tiles, the brake lines, and things of that sort. So what we did was we went through to make sure and evaluate the bare earth, the brake line collection, the classifications, the information met the requirements as we kind of detailed as far as for the scope. Everything looked great. So and once that got passed on through, obviously they made all their deliverables and things of that sort. So I just wanted to kind of give you that kind of a background. So what's the more important role is, now the evaluation of what does 30 points mean, and how does that change our topology or our expectation. This is what I think is probably was more eye-opening for me in what I thought what LiDAR was, say 5 years ago, 10 years ago. I thought, oh, this is great. Well, this takes it to a kind of a whole new step and a whole new level. So this was something that I was really taken back, with the level of detail and how the information looked, because we have a 2015 data set that was 4 points per meter squared. So it was something that we could evaluate directly and say, okay, how does that compare? What does that look like in relation to the data set that now we're getting, with regards to this high density, solution. So, so next slide. So looking at the first part, this was just as we zoomed in, I just to give you kind of an ortho backdrop, and then providing the 1 foot DEM and how that compared, that just related to the ortho, which was extremely tight as far as which was confirmed by the horizontal, and things of that sort. You can see the detail. You can see the curved lines and things of that. So next slide is the 2015. That's what it looks like in comparison. It still is good, but you can see it's definitely, the resolution is significant, and you can kind of start to understand what you get with high density. It's the same thing with a 3-inch pixel versus a 12-inch pixel. Resolution is key, and the more information is picked up and denoted and determined. So so it's just to give you some comparisons. So here's kind of a quick side by side, and you can see how the features haven't changed, but the resolution is obviously significant. So that just shows kind of and demonstrates the capabilities of what high resolution means and how it directly reflects to topology. So next slide is just kind of here's another area. This area, instead of being urban, this was kind of looking at it more from the braided stream and the rural, or, kind of, so to speak, it's Milwaukee County. So there's not a lot of rural, but but we're looking more into the area, river area. So it's one of those where with the braided stream. So you can kind of, everything looks, was great. But again, how does that compare? So next slide. I kind of zoomed in on the braided stream aspects. You can definitely see how the cuts and the changes and what it looks like. Next slide. Here's what it looks like at 4 points. You can see it's there. It's not that it's the information is certainly not is being represented. Just the clarity and detail is somewhat lost. So you can definitely see the differences. So again, just doing a quick comparison of between both what it looks like at 30 points versus 4 points. So that was some of the things that we wanted to. So you could definitely see the 2015 as it relates to 30, or at 2020 between 4 and 30. There was definitely a much bigger dramatic difference than I had really expected in the surface modeling, and that was an interesting point of view. So now we wanted to look at, so how does it look with regards to the above ground features? And this was the more, I think this, in my opinion, is the more telling tale. So here is 2015 and what it looks like with, you can see that the sides are not there. The building tops are good. Everything looks, really good. Well, next slide. Here's what 2020 looks like. Now you start to understand the tree that is, the detail of the tree is much fuller. You now have the building sides, talking about that oblique, perspective, and things of that sort. So next slide. Here's another area, just, profiling. You can look at the trees, as far as just to give you kind of clarity. This is 2015, and then here's 2020. You know, you can see the branches now. You can see the level of detail that, you know, if you're looking for the top, well, that's no problem. But if you're looking for the information that's on the sides, the crown, and things of that sort, obviously that's going to open up a lot of eyes. So again, you know, it's just, you know, the amount of detail and the resolution that's achieved. Tree canopies are well defined, crowns are, you know, easily measured, you know, roof lines are defined. Wall points can easily be, you know, with the help of now constructing 3D buildings, et cetera. So those all, you know, provide great detail. So just to give you that heads up. So I know we're running late, sorry.
Okay, thanks, Rob. And Jim, we just have 2 slides left, I think.
No worries, keep going. You started a little bit late, so you're good.
Sure. We wanted to, you know, some of the real value coming out of a project of this nature is the ability to go in and derive additional information, especially above the ground. So, you know, one thing that there's a list of items here, and culverts can be extracted, and those can be used to hydro enforce the DEM, certainly improving hydro. So for this project, we can go in and collect flowing water down to 8-foot streams and ponded water to 1-acre ponds. So you really have a really highly detailed hydro break line collection. In the graphic on the screen here, you can see 3D buildings that have been extracted from this data. And I think you saw in some of Rob's slides there, you know, the ability and the point definition on the building rooftops as well as the sides of the building. So this is a relatively new process to be able to extract 3D buildings in a mostly automated fashion from this density of LiDAR. And you can see the level of detail that it captures. Certainly contours, you know, down to a 1-foot contour level. And then bare earth point data sets are, you know, still very important to be able to take that high density data and create a DTM essentially that can be used in engineering type applications. And of course, the list goes on, but those are some examples of derivatives we wanted to bring up because they're relevant to this project. Because what we have going on here is many stakeholders can become involved in a project like this. So once you go to this higher point density, it opens up a lot of options above and beyond, you know, maybe a previous quality level 2 LiDAR data set. So you can really bring in and bring value to other departments and other, you know, potential stakeholders in the project. So, you know, transportation engineering certainly is one. We've heard a lot about enhanced hydrography, parks and rec, when you have the ability to see those tree canopies. You can really analyze street trees, for example, and really important trees that you have in parks around the area. Forestry applications are significant. Coastal and river erosion. You know, I think Milwaukee County, certainly along the shoreline and along the bluffs, there's erosion happening that can be modeled to a high level of detail. Public works, you know, now we're talking about being able to extract utilities and things that are important for public works, and then water and sewage districts in terms of culverts and how the water's flowing and things of that nature. Anything to add on stakeholders, Rob?
Other than, you know, we've been able to work with, you know, the DOT and, you know, MMSD, so that I thank them, and, you know, trying to look at and exploring other options. So it's not just, you know, the county, it's other agencies within, you know, that might have other greater uses, which is opening up other doors, as you mentioned.
Okay, that concludes our presentation for today.